All right, so today we're going to start polar coordinates, and we'll be spending a few days on the relationship between rectangular and polar. So rectangular is what you have been used to all along. That's the Cartesian coordinate plane. And so the x-coordinate is your horizontal movement, and your y-coordinate is your vertical movement. And so when you graph a particular point, you would go in a certain direction, either left or right, x units, and then you would either go up or down y units. So you could have a positive x coordinate, a positive y coordinate. You could also have a point where you would have a negative x coordinate. You could also have a negative y coordinate, or a combination of any of those. The special point that we refer to is the distance from the origin, which is located at 0, 0. And so you could be a horizontal distance away, you could be a vertical distance away, you could even measure a diagonal distance away from the origin. All right, so now we're going to shift over to polar coordinates. So polar coordinates, instead of x, y, are r, theta. So r is the radius measured from 0, 0. We're not going to call it the origin anymore. We're going to call it the pole. So think about on Earth, there's a North Pole. Think of if you were to look at an overhead view of, like you're out in outer space looking down at Earth and you're staring directly at the North Pole. That's where this center is located. All right, and then theta is the angle that's measured from the polar axis, which is on the right side here. Essentially think about it as your positive x-axis and how you measure angles either being positive or negative, opening upwards or downwards. So regarding the first coordinate, that's the radius. So imagine if you were 1 unit away from the pole in any direction, and I were to create a circle that is exactly 1 unit away from the pole. That has a radius of 1. If I were 2 units away from the pole and created a circle, then that would have a radius of 2, and so on. When you plot points on the polar coordinate plane, you're going to start with the angle first. It's measured in radians, and then you're going to count the number of circles away from the pole. In this case, it would be 4 circles outward from the pole. All right, so now we have to figure out where is pi over 3. So we know that when we are looking at radians, it's 0, and then pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. So nothing changes there. Halfway between 0 and pi over 2 is pi over 4. So I'm going to label those. We've got 3 pi over 4. Pi is 4 pi over 4. This is 5 pi over 4. 3 pi over 2 is 6 pi over 4. And then this would be 7 pi over 4. So halfway in between where the axes are, those are your whatever over 4. All right, so now I'm going to label in every pi over 6. So pi over 6 is, think of it as 30 degrees. It's a little bit less than pi over 4, so this would be pi over 6. This would be 11 pi over 6. This one would be 7 pi over 6. This one would be 5 pi over 6. And so that's just pi over 6 upwards or downwards from either 0 or pi. And then I'm going to label in the pi over 3, which would be 60 degrees. So that's more than pi over 4. So this is pi over 3. And then we've got 2 pi over 3. And this would be 4 pi over 3. And then this one would be 5 pi over 3. All right, so you'll notice that some of these are not labeled. I'm just putting an X to indicate that these are not labeled. So we only want values that are on the unit circle, like multiples of pi over 6, multiples of pi over 4, multiples of pi over 3, and multiples of pi over 2. Then we're not going to label some of these additional angles. So I'm going to erase those actually. So now let's actually label point A. So we're going to find where is pi over 3. That's right there. And then when you find pi over 3, count 4 circles outward. So 1, 2, 3, 4. So this is point A. All right, the other thing you should know is that unlike on the rectangular coordinate plane, if there's a point at 3, 2, there is only one name for the point at 3, 2. You can't call it anything else. However, with polar coordinates, we could have also called point A 4 units away from the pole, but we could have gone in a negative direction, and we could have gone negative 5 pi over 3, and that would have ended up in the same location. So since we have coterminal angles, technically there's an infinite number of coterminal angles that would end up at this exact same location where point A is located. And then I'll show you some more answers for point A after we go through point B, C, and D. All right, so for point B, we're going to find 11 pi over 6, which is right here, and then we're going to go outward 2 units, and so this is point B. So it's 2 circles away from the pole. All right, and again, we could have called point B, that would have ended up in the exact same spot if we had graphed 2, negative pi over 6. All right, for point C, we're going to go to 5 pi over 6. When you see a negative radius, that means you actually want to travel over the pole, like so cross over the pole and go 2 units on the other side, but still on this same line. Right, so I've highlighted this line, and so I want to just label this point C. And you'll notice that it ends up exactly in the same location as point B. Another name for point C, another location, we could have gone downward in a negative angle, so we could have done negative 7 pi over 6 and then crossed over the pole. So if we went negative 7 pi over 6, we would end up at 5 pi over 6, and because we have a negative radius, we would cross over the pole and end up on the other side along that line that's highlighted there. So for point D, we're going to find 4 pi over 3, so here's 4 pi over 3, and we're going to go 4 units outward, 1, 2, 3, 4, so we're 4 circles or 4 units away from the pole, and so this is point D. So what are some other locations that would end up in the exact same spot as point D? Well, we could have gone in a negative angle, and we could have gone negative 2 pi over 3 and ended up at 4 pi over 3, and so we would still be 4 units away from the pole. The other thing we could have done is I've highlighted that line in pink, and we could have been on the other side of the line and then crossed over with a negative radius. So to get to that other side of the line, we could have been at pi over 3 and then had a negative 4 as a radius, or we could have also gone negative 5 pi over 3 and then gone with a negative 4 radius, and it would end up in the same location as D. So what you're going to see is that there's going to be multiple answers for a single location or point on the polar plane. Let's go back to point A. So what else could we have done? We could have been at 4 pi over 3 and then crossed over the pole and gone to negative 4. And then we could have also been at, we also could have gone in a negative direction to negative 2 pi over 3 and then crossed over the pole that way and ended up in the same spot as point A. So if you imagine that the polar coordinate plane is just an overlay over the x and y coordinates, you can see that we're going to convert from polar to rectangular or rectangular to polar, and we're going to end up in the exact same location, but sometimes we use the polar coordinates and sometimes we use the rectangular coordinates. All right, so for some of our basic formulas, we may need to convert from rectangular to polar, not just with coordinates, but also with equations. So we know that a point on the rectangular coordinate plane is x comma y. So I'm going to draw this out. This is my x-axis, my y-axis. So if I have some point over here, I go x along the horizontal axis, and I go y vertically. And I could draw in a right triangle and do a hypotenuse of r, which is my radius. This is my angle theta, which we know opens upwards. All right, and we could then create any kind of trig ratio that we want using opposite, adjacent, and hypotenuse. And then we also know things such as x squared plus y squared is equal to r squared from the Pythagorean theorem. All right, so let's say I wanted to figure out what is sine of theta. Sine of theta is the opposite over the hypotenuse, which in this case would be y over r. And so we could convert, and we're going to use the equation. If I multiply both sides by r, I would get r times sine of theta equals y. So we're going to use this equation sometimes to convert from polar into rectangular. And then for cosine of theta, we know that that's adjacent over hypotenuse. So that is equal to x over r. And if I multiply both sides by r, then I get another conversion equation, which is x equals r times cosine theta. And then if I wanted to figure out what is tangent of theta, I could either do opposite over adjacent, which we know is y over x. If we wanted to verify the Pythagorean theorem, we know that x squared plus y squared equals r squared. So x squared is r cosine theta. We could square that. Y is r sine theta. We could square that. And we know that r squared is just itself. So if I squared everything, I would get r squared times cosine squared plus r squared times sine squared. And if I factored out an r squared, I would get r squared times cosine squared plus sine squared. And we should know at this point that cosine squared plus sine squared is equal to 1, so r squared really does equal r squared. Another thing we could verify is that tangent of theta, we know that is opposite over adjacent, which in this case, according to that triangle, is y over x. And we could use our equations from above, r sine theta over r cosine theta, and we know that tangent of theta is sine over cosine. So we're going to use some of these basic formulas to answer some of the questions on the next page. All right, so as a reminder, we want to graph the angle first. So we have to find where 2 pi over 3 is. So here's 2 pi over 3. And then we want to be 1, 2, 3 circles outwards. So I'm going to label that as point A. If I want to convert this into rectangular, I'm going to use the formula x equals r times cosine of theta. So my radius is 3. Cosine of theta is 2 pi over 3. And then this is where you need to think about the unit circle. So when it's 2 pi over 3, cosine is my x coordinate. Sine is my y coordinate. So cosine is the shorter one, so that's negative 1/2. So this is 3 times negative 1/2. And so my x coordinate would be negative 3 over 2. I'm going to do the same thing for y, so that's r times sine of theta, which is y equals 3 times sine of 2 pi over 3. And the y coordinate is the longer one, so I know that that's root 3 over 2, and it's positive. So really the polar coordinate plane is just on top of the rectangular plane in this case. We can visualize it here. And we've got 3 root 3 over 2. And so if I were to convert my coordinates from polar into rectangular, now I've got the ordered pair negative 3 over 2, comma 3 root 3 over 2. All right, for point B, I need to find where 11 pi over 6 is. And then I need to be 4 circles out. So this is point B. All right, now I need to convert that. So I know my radius is going to be 4. And then my cosine is my x coordinate. That's the longer measurement. And then my shorter measurement, that's negative. So I'm going to have a positive root 3 over 2 and a negative 1/2. So if I simplify that, I get 2 root 3 and negative 2. All right, so point B is at 2 root 3 comma negative 2. And then I'm lastly going to do point C, which is negative pi over 6. But if you notice, if you go negative pi over 6, you end up in the exact same spot as 11 pi over 6. And when I'm 4 units outwards, I'm in exactly the same location. So point C and B are the same, which means that point C is also 2 root 3 comma negative 2. So we know that 0, negative 2 is x comma y. And now if we're trying to convert into polar, if we use this equation, we know that x is 0. The radius, let's figure out what the radius is. So we know that x squared plus y squared is equal to r squared from Pythagorean Theorem. So 0 squared plus negative 2 squared is equal to r squared. And that 4 is equal to r squared. And if you take the square root, you would get plus or minus 2 equals r, but they said it had to be non-negative, so we're going to go with r being positive 2. So I'm going to fill that in. So now I divide by 2 on both sides, and I get 0 equals cosine theta. So we're going to use that eventually to help us figure out what angle would have an x-coordinate of 0. Right? And then if we go to y equals r sine theta, y is negative 2, r is positive 2, and then if I divide both sides by 2, I get negative 1 equals sine of theta. All right, so let's think about the unit circle, 0, negative 1. I would go 3 pi over 2 in radians. So the ordered pair would be 2 comma 3 pi over 2. If I were to verify that on a polar coordinate plane, 3 pi over 2 is down on the bottom, and I'm 2 units away from the pole. And then rectangularly, I go 0 right and left, and I go down 2 units. This is the rectangular coordinates, and then this is the polar coordinates. In order to be in rectangular, we need to have only x and y as our variables. So one trick is to multiply both sides of the equation by r, and if we do that, we get r squared equals r times 2 cosine theta. Now I'm going to rearrange that and write it as 2 times r times cosine theta, and this is r squared. And so now think back to your basic formulas. R squared can be substituted with x squared plus y squared, and then r cosine theta can be substituted with x, so this is equivalent to 2 times x. Now, this answer is okay because it has x's and y's in it, so it is technically rectangular, but a better way or a more simplified way would be to maybe complete the square. So if I move everything over with x squared minus 2x plus y squared equals 0, I can complete the square and I get x squared minus 2x plus something, and then plus y squared equals 0 plus something. So to figure out what that something is, take half of negative 2, that's negative 1, and I square it, and that's 1. So whatever I add to one side, I add to the other side. And then if I factor, I get x minus 1 squared plus y squared is equal to 1. So for number 4, it's a little bit different because we have cosine of 2 theta. So if we use our identities sheet and try to simplify or substitute, we can replace cosine 2 theta with cosine squared minus sine squared. So I'm going to do that first. And then now I need to try to get x and y substituted in there. If I only multiply by r, I would get r squared equals 3r times cosine squared minus sine squared. And if I distribute that, I would get 3r cosine squared minus 3r sine squared. So that's okay, but this does not substitute as x or x squared. So I'm a little bit short, and I need another r. So I'm going to multiply by another r. So really I could have multiplied by r squared to begin with. And I'm going to get r cubed equals 3r squared cosine squared minus 3r squared sine squared. And then I can use my equations to substitute. So r squared cosine squared, just like r cosine theta was x, r squared cosine squared is going to be 3x squared. And then similarly, this will be minus 3y squared. So replacing the r cubed, that's a little bit tricky. I'm going to replace r cubed with r squared to the 3/2 power. And the reason for that, I'll show you in a minute, but when you remember exponents to exponents, 2 times 3 over 2, that gives you 3, so that's how we can replace the r cubed. But what we needed was something that can use x squared plus y squared equals r squared, like we did in problem number 3. So I'm going to change this to be x squared plus y squared, and I'm going to raise that to the 3/2 power, and it equals 3x squared minus 3y squared. Now this equation is a little bit ugly, but it is technically in rectangular form because it does have only x's and y's. All right, so everywhere where we see an x, we're going to replace it with our formulas. So x can be replaced with r times cosine theta, and y can be replaced with r times sine theta. And then we can just make it look a little bit nicer. So I've got 3r cosine theta minus 4r sine theta equals 2. And then typically you will solve for r. So if I factor out an r, I've got r times 3 cosine theta minus 4 times sine theta equals 2. And if I divide both sides by this quantity that's in the parentheses, I've got 2 over 3 cosine theta minus 4 times sine theta. And that's solved for r, kind of like how you solve for y equals in rectangular form often. But technically, even back at the first step, that was in polar form. You just might not find that on a multiple choice test listed in that manner. All right, so for our last problem, let's try to replace some things. So x squared plus y squared equals r squared. And then x squared and y squared, remember x is r times cosine theta, so we'll just square both of those. And then y is r times sine theta, so since it's y squared, we're just going to square both of those. I could divide by r squared on both sides. That'll cancel those out. And then I can also divide by cosine squared on both sides. So now I'm left with r squared equals sine squared over cosine squared, and that's familiar because r squared is equal to now tangent squared. Could even square root both sides and make it even more simplified, so we've got r equals plus or minus tangent of theta. So depending on if it's a multiple choice test, you might see it listed like this. You might see the r squared equals tangent squared. You could even see it listed as our first step, because technically that is in polar form since it doesn't contain any x's and y's, and it only contains r's and thetas. All right, so if you have any questions, make sure that you ask your teacher. Have a nice day.